Yes. I've seen the first one of the new set because I saw the original 3 when they came out, and then the 2 that followed it, and then the new one. I haven't seen the last 2. So I've seen 5 of them. All right, guys, are there any questions on any of the assignments thus far? Any questions on any of the assignments from factoring worksheets 1 and 2? All right, guys. So what we're doing today is covering factoring of kind of the special factors. These ones that we cover today kind of factor in a special way or kind of a unique way. Now, the first one that we look at really isn't too special in how we do it. It just works out to have a unique way that it factors. We were given a set of a theorem for this here, really talking about that a squared, not a squared, that a plus b squared is going to be the same as a squared plus 2ab plus b squared. We also have that a minus b squared is going to be a squared minus 2ab plus b squared. So if we know that we have a quadratic in the form of a squared plus 2ab plus b squared, it will factor into a plus b squared. Or if we have it in the form a squared minus 2ab plus b squared, it'll factor to a minus b squared. But it's almost going to take as much time to factor it that way as it would be to actually just do it the way that we were. So it's not going to save us any time kind of memorizing those formulas and then working it out that way. For these here, it's almost going to be just as effective to do our 2 sets of parentheses with 3 spaces and factor it this way. Now, 2 of the sets that we'll factor today will work better and easier with the formulas and seeing how they work that way. These really don't save us any time. Now, there isn't a greatest common factor between these 3 terms, so we're just going to move on to our 2 sets of parentheses. Now, since the third term is positive, the signs are the same and they match the sign of the middle term, which is negative and negative. Then we're going to find the factors of the first and third term. Now, our first term is our 4x squared. Well, for x, we're going to have x and x. And for the factors of 4, we have 1 and 4 and 2 and 2. Which one do we want to try first? 2 and 2. Well, now our other term is 1. Well, the only factors of 1 are 1 and 1. And lastly, we can check to make sure we got this set up correctly. So 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x. And negative 2x minus 2x is negative 4x, which is the correct middle term that we wanted. So these here are the factors of this trinomial. But we can actually rewrite them in a different way, because we could rewrite this as 2x minus 1 squared, because both of those sets of parentheses are the exact same. And whenever we square, we're just saying it's times itself. That's kind of why this one here is special, because it works out that the factors can be rewritten as one set of parentheses squared. That's the only reason that this is kind of special or unique. Any questions on this here? This really didn't, these here aren't any real different than what we did yesterday and the day before. It just works out that their answer is one set of parentheses. Any other questions on this here? We'll look at one more of these and then we'll move on. Yes? Yes. So we'll look at this one here and then we'll move on to a different type. Now, if we look at this one here, we need to see if there is a greatest common factor between these 3 terms, which, well, unfortunately, there's not. So we'll have our 2 sets of parentheses with 3 spaces. we'll find the sign. Since the third term is positive, the signs are the same and they match the sign of the middle term, which in this case would be negative and negative. Now we need to find the factors of the first and third term. Well, the first term is 16b squared. Well, we know for certain that we will have b and b as the factors. And if we look at the factors of 16, well, we have 1 and 16, 2 and 8, 4 and 4. So which set of factors would we want to try first? Well, probably the 4 and 4, right? Because if we're wanting them to both be the same, we'll use 4 and 4. Now our third term is 25. So we'd have 1 times 25 and 5 times 5. Most likely we're going to use 5 and 5 because we knew these were going to be special. So most likely they're going to turn out to be the exact same thing, and that actually works out to be the case here. 4b times negative 5 is negative 20b. Negative 5 times 4b is negative 20b, and negative 20b minus 20b is negative 40b, exactly what we wanted. So these here are the factors, or we can really rewrite it as 4b minus 5 squared. Either one works, because it works out that these are actually the exact same answers. Any questions on any of this here so far? Now, we're not going to work through this one here because it's going to work almost the exact same as what we just did. The only difference is that the symbol or sign in the middle is going to be plus instead of minus. That's the only real difference. So any questions on this here before we look at the next type? N squared minus 25. And we've covered this type before, and this is actually considered or called the difference of perfect squares. And the main formula for the difference of perfect squares is talking about a squared minus b squared will be factored in the form of a plus b times a minus b. So any one that follows or is a difference of perfect square will come in the form of a plus b times a minus b. And really our a and b are whatever number that is being squared. So if we applied that here, so what squared or what times itself will give me n squared? N, because n, if we can write in kind of the notation n squared, a squared would be that there. Now what times itself will give me 25? Well, it would be 5, because 5 squared is 25. So what that's telling us is that this is the difference of perfect squares. And if we follow this set formula, really it's saying that this is going to be what? N plus 5 times n minus 5. And that's it. And really these difference of perfect squares will always work in the same fashion. Any questions on this here? So let's look at this next one here, 16n squared minus 9. So we do have a difference. Now the question is, are both of these perfect squares? So what times itself would give me 16n squared? For n. And what times itself would give me 9? So this would factor to be what? 4 times. And that'd be it. Now, technically, what we could also say 4n minus 3 times 4n plus 3, because with multiplication we can multiply any two things in any order. So the order in which we do the plus, put which one first, really doesn't matter. We just have to have one with plus and one with minus. And that's it. And normally I find that most students like the difference of perfect squares factoring it more than most because it's a little bit easier to do. Any questions on this here? So we feel comfortable with this? Now we do have two things being subtracted, yes? It'd be nice if they were a difference of perfect squares. So is 9 a perfect square? It would be 3. Is a to the 4th a perfect square? And what times itself would be a to the 4th? Because a squared times a squared, whenever the bases are the same, we add the exponents. So a squared times a squared would be a to the 4th. We could also think of it as a squared squared, because powers and powers multiply. Bless you. And we would get to the same thing. So this is still a difference of perfect squares. And how would we factor it? It would be a squared plus times a, exactly, a squared plus 3 times a squared minus 3. And we're only really looking for the rational factors because, I mean, we could probably try to solve this here, but we would have irrational and imaginary or complex solutions. So this is as far as we can take this here. Now we do need to be a little bit careful with this one here, just in case both of these are perfect squares. Now in this case here, a squared is a perfect square minus 3. Is 3 a perfect square? Well, no, there's not a number, whole number that's being multiplied by itself that'll give us 3. So we can't do anything from there. But if one of those was a perfect square, then we could actually take it a step further. And we'll see one of those in a minute. Any other questions on this here before we look at the next one? Let's look at the next one here. Is this here a difference of perfect squares? Well, yes, because 36 is going to be what? 6, and our k to the 4th is k squared. So really this can be factored to what? Times k squared minus 6. And for this one here, that would be as far as we can take it. Any questions on this here? Okay, you're going to have to add one to the note sheets, and that's going to be this one here. As we've kind of mentioned so far, x to the 4th is really x squared squared. And 81 is 9. So if we factored this, we would have what? X squared plus 9 times x squared minus 9. But 9 is a perfect square. So that means that this here, x squared minus 9, is still a perfect square that we can factor. So this here wouldn't be factored completely. We'd actually have to take it one step further. So here it would be x plus 3 and x minus 3. and then this would be factored completely. Because the x squared plus 9 is actually not a difference of perfect squares. It would actually have complex roots if we went on and factored it. We'd almost have to solve it to be able to factor the x squared plus 9. It doesn't come out nicely. Any questions on this here? Not too bad. Because we didn't get around to actually covering this here. We were going to cover these more in the chapter 4 before the break, but we just didn't have time to cover these. Any questions on any of this so far? All right, now this here isn't in the note sheets. I wanted to put this up and show this to y'all because we didn't get to cover the sum and difference of perfect cubes or factoring by grouping. We were never able to cover these two, just mainly because we didn't have time. Normally I would cover them in chapter 4, the chapter we had before the break, but unfortunately we were just a few days short. So whenever we're looking at these here and factoring them, it's always going to be the same, opposite, always end on a positive note. And it works for both of them. Now the other main part is that we have a squared, a to the first, and here is really a to the 0. Then we have b to the 0, b to the first, and b squared. So whenever we're looking at these here, we're really going to take the cubed root of both to find a and b, and then plug it in accordingly. Now, let's go on and look at the first example, because once we start doing some of these here, they're going to be easier than you actually think they might be. Now, the first main step to these perfect square or perfect cubed difference, tripping all over my own tongue, the sum and difference of perfect cubes is taking the cubed root of the two terms. Because what this does is one of two things. The first is that it tells us and helps us be able to see, is it a sum or difference of perfect cubes? The other is it helps us find the values of a and b that will be plugged in. Now when we look at this here, the cubed root of x cubed would be just x. Because whenever the root and the exponent are the exact same, they cancel out. Now we need to find the cubed root of 125. Well, we can actually do this here on the calculator. Because the graphing calculators, if we want to plug this in, we can hit math, and the fourth one down is the cubed root. So on the yellow calculators, if we hit second and the little caret key, this button here, it will give us a radical that we can actually take the cubed root of. So if we hit enter here, cubed root of, I think it was 125, and hit enter, tells us that it is 5. So here, the cubed root of 125 is 5. So that tells us that this is the sum of perfect cubes. And we can actually factor this. So we can go on and set up our parentheses. Now I think of these parentheses as a tractor trailer, because the first one is going to have 3 spaces, and the second is going to have 5. So I think it kind of looks like a tractor trailer. Any questions on this so far? So, like with any of the other factors, we're going to find the signs next. And the signs for any of these here are going to be the same. Opposite always end on a positive note. So our starting sign is plus. So if it's the same, we're going to have plus. Next one is opposite, so it would be minus. And we always want to end on a positive note. So here we're going to have plus, minus, plus. Same, opposite, always end on a positive note. And with any of these here, we're always going to have 2 plus signs and 1 minus. That's just how it's going to work out for any of these here. Now, any questions on this? Now we're going to be using the x and 5 to plug in to get the numbers in terms. Now since x cubed was first, x is going to be going in the first spots. So for here, we're going to have just x to the first. Now inside the bigger set of parentheses, our first one here is going to be x squared. In the next spot, it's going to be x to the first. And in the last spot here, we have x to the 0. And I wrote it a little bit above it because really after this one here, I don't really include it. And that's because x to the 0, anything to the 0 power is 1. So it's not really there. We're just multiplying by 1. And the reason I include this is because if we look at the powers with x, it's going 2, 1, 0. They're decreasing down. Now we can look at our other terms. So in the first one, we're going to have 5. And in the bigger one, the first part here, I'm going to write it up a little bit to the top. We'll have 5 to the 0. Well, 5 to the 0 is just multiplying it by 1. Now in the middle, we're going to have 5 to the first. And what do we think over here is going to be 5 second? Now if we notice with the second term, it's going 0, 1, 2. So as the one is decreasing, the other is increasing. Any questions on this here? Because we only have one step left. You ready for the last step? And that's just simplifying. So here the x plus 5 doesn't have anything that's going on. The main simplification is going to be in the bigger set of parentheses. And the first thing we have is x squared, which is just x squared. The only time it'll really change is if we have a number with x. So if inside that parentheses was 2x, then we would square both the 2 and the x. Minus, here we have x times 5, which would be 5x, plus 5 squared is 25. And that's it. A little bit easier than what y'all thought this was going to be. Maybe a little bit. But that's all we have to do. Because once we find the two terms, we set it up and just plug it in respectively. Any questions on this here? We have a few more that we'll do. Let's look at this one here. X cubed minus 64. We're going to take the cubed root of both of them so that one, we get the two terms that we need, and the other is to see if it is a difference of perfect cubes. Well, the cubed root of x to the third is, well, just x. Now the cubed root of 64, now if we go over to the calculator, we can plug it in and check and see what it is. So I can go math and scroll down to the cubed root, type in 64, and we get 4. Because 8 squared would be 64. 4 to the third is the cubed root. So this here would be 4. So that means that this is the difference of perfect cubes, and we know exactly what their cubes are. So we can set up the tractor trailer. So our first set of parentheses with 3 spaces, and the second set has 5. Now we need to plug in the signs, which is the same, opposite, always end on a positive note. So we would have minus, plus, plus. Because since we started out with minus, the same would give us a minus. Opposite would give us a plus. And we always want to end on a positive note, so it would end in a plus. Okay. It's plus. Okay. Yeah, I'll need to fix that. Oh. Yeah, I wrote them a little smaller. I need to give them all numbers and make them a little more significant so they're easier to see. And maybe make the next one a little bit more different than this. So they're not both look like they're both x cubed and 64. Now, if we're plugging in the first term, well, we're going to have x, and then this here is going to be x squared, x, and then the last one's x to the 0, but anything to the 0 power is 1. So we don't have to write it in since it's going to be a multiplication of 1. Now the next one we'll look at is 4. So here we'll have 4. Well, with the x squared, it would be 4 to the 0. Then in the middle, we would have 4 to the first. And lastly, we would have 4 squared. And if we simplified this down, we would have x minus 4 times x squared plus 4x plus 16. Any questions on this here so far? The sum and difference of perfect cubes, not too bad. We're ready for the next one. I changed it a little bit because as I started noticing this here the first time I did it, which I really hope was last year, but I have a feeling it was the year before, which means I didn't change these note sheets twice. I changed it 3 years ago, but apparently just didn't get around to changing the note sheets. And what I noticed is that every single one of these, the term that went first, whatever had the variable, had 1 with it. It really didn't tell us with a number. But I wanted to show y'all one where we actually had a number with both. Now, when we look at this here again, we're going to take the cubed root of both terms to help us, one, see what the two terms are going to be that we plug in, as well as being able to determine if it is a sum or difference of perfect cubes. Now, unfortunately, we can't just plug in the cubed root of 27a to the third because, well, a to the third is a variable, and in both calculators, we needed to have a specific value. But we do know that a cubed, the cubed root of it would be a. Now, we can plug 27 into the calculator. So we can come over here and do math and pull up the cubed root and type in 27 and hit enter, and it'll tell us that the cubed root of 27 is 3. So this here would be 3a. The cubed root of 27a to the third is 3a. Now the cubed root of 64 is 4, because we did find that one already. So this does work, and we do know what both of our terms are. So the next part is finding the signs, which would be the same. Opposite always end on a positive note. So we would have plus, minus, plus. Then we would plug in 3a first, so we would have 3a. This here would be 3a squared, 3a to the first, and then the last one would be 3a to the 0. And then we can plug in the 4, which would be 4 Next one would be 4 to the 0. Our middle one would be 4 to the first. And our last one would be 4 squared. Any questions on how we plugged any of this in? And lastly, we can simplify this down, which would tell us that we have 3a plus 4. 3a squared, well, 3 squared is 9. And then we would have a squared. 3a times 4, well, 3 times 4 is 12. We have a plus 4 squared is 16. And we get this here. Any questions on any of this here so far? Not too bad. All right, let's do one more of these. After we do one more, we'll be done for today, and we'll leave the factoring by grouping for tomorrow. Well, fortunately, I added another one in. Luckily, I have actually fixed the note sheets now, but that doesn't do us any good at this point. Luckily, with both of these here, taking the cubed root of 192x to the third, well, I know that the cubed root of x to the third is x. And for the other one, the cubed root of y to the third would be y. So we can do those pretty easily. Now for 192, I would come back over to the calculator and have it do it for us. So we can go math down to our cubed root and type in 192 and hit enter, and it tells us, well, it's 5.78 or 768998281. So it's not a perfect cube. Math 481. It's not a perfect cube either. So let's look back at it. Is there a number that will go into both 192 and 81? Three will. Because 81 is 9 squared, or it's actually 3 to the fourth. 192 is actually 3 times 64. 81 divided by 3 is 27. So it worked out that the original 2 did not have perfect cubes, but our new 2, 64x to the third, these here will work. Now we've already found 64 once, because the cube root of 64 is, well, 4, and x cubed would be x. The cube root of 27y cubed, well, 27 we found to be 3, and the cubed root of y to the third is y. So we have these two here. So that means we can factor this. Now we still need to keep the 3. As we still need it when we factor these. Now the first thing we can find is the signs, because they're going to be the same, opposite, always end on a positive note. And since our starting sign was minus, it's going to be minus, plus, plus. Same, opposite, always end on a positive note. Now we can plug in the first set of terms, which is our 4x. So we'll have 4x. Here we're going to have 4x squared, 4x, and then 4x to the 0. And for our next set of terms, we're going to have our 3y. So in here we would have 3y. 3y to the 0. In the middle, we'll have 3y to the first. And the last one, we'll have 3y squared. And lastly, when we finish this up, we're going to have 3 times 4x minus 3y times, well, 4x squared. 4 squared is 16. And well, x squared is just x squared plus 12. 4x times 3y. 4 times 3 would give us 12. And we would have xy plus 3y squared. Well, 3 squared is 9, and y squared is y squared. And that there would be the answer. Now, I will say if one of these ended up showing up on the ACT to factor this here, factor it down, one of the nice things is even if you don't remember all the steps, if you remember at least how to find the signs for them, that'll help eliminate some of the answers. Same, opposite, always end on a positive note. Because any way you can eliminate possible answer choices on the ACT, the better off. Also, I'll mention this especially next time. The quadratic part, the bigger part of this sum or difference of perfect cubes, will always have complex solutions. That means the solutions will contain I every single time. It will only have one real solution, and that will be the linear part, the smaller part, will be the real solution. The quadratic part or the bigger part will always have complex solutions every single time.